Hi there, this is lesson 5 of Unit 4, Applications of Exponential and Log Functions. We're looking at the log scales and their applications. So the Richter scale is a very common log scale to the base 10. And the scale, if you increase from a magnitude of say 8 to a magnitude of 9, you've actually increased the intensity by a factor of 10. So it's saying here that the Richter scale is named after the American seismologist Charles Richter, and it's used to measure the magnitude of an earthquake. Magnitude of an earthquake is a measure of the amount of energy released. It is determined from the log of the amplitude of waves recorded by the seismographs. The Richter scale is logarithmic, a difference of 1 unit in magnitude, and these are the differences in magnitude here, corresponds to a factor of 10 difference in intensity. This means that each whole number step represents a tenfold increase in intensity. So a magnitude 9 is 10 times more larger in intensity than a magnitude 8. And a magnitude 9 earthquake is 100 times larger than a magnitude 7 and 1,000 times larger than a magnitude of 6. Basically, you can think of these differences as you're logging, it's a bit too thick, you're logging the difference between 9 and say a magnitude 7. So actually, sorry, erase that. It's not quite what I meant to do. I'll just work down below. We're looking at magnitudes here, so if there's a difference of 2, so magnitude of 9 earthquake compared to a magnitude of 7, the difference between the two is really in intensity, it's a difference of 100. So, I'll let you read the rest of this here as I scroll down to probably the first example here. So in actual fact, the first example you could probably do yourself, so I'll let you fill it in now, if you just turn to that, and then I will just scroll down to the answers and you can check your answers. So pause your video right now and see if you can fill that in. Hopefully you have your textbook with you. Okay, so an earthquake of magnitude 8 is 10 times more intense than 7. Earthquake of magnitude 7 is 10,000 times, or 10 to the 4 times, more intense as an earthquake of magnitude 3, and so on. So check these answers, and we'll go to the next. So in comparing intensities and magnitudes, basically we can look at the magnitudes of M1 and M2. A magnitude of an earthquake is given by this formula. Magnitude is equal to the log of intensity of an earthquake divided by the intensity of some reference, whatever that might be. Or it just might be the intensity of one earthquake compared to another. And therefore this M value is the difference in magnitudes between the two earthquakes of intensity I and intensity 0. So here they're just, for example, calling the magnitude of one earthquake M1, and here's the log of the difference of intensities from some reference point, I0, compared to I1. And another magnitude, again, compared to the same reference I0 and its intensity I2. It's asking you here to show that M1 minus M2 is equal to log I1 over I2. For this, it's pretty trivial. I'll let you look at this and then hence show that I1 divided by I2, which is what I've really been saying in the previous page, is really 10 to the exponent M1 minus M2, the difference in magnitudes, 10 raised to that exponent. And so if the intensity of one was greater than the intensity of the second one, M1 would have a higher magnitude than M2, and this would be a number above 1. So if M1 was, say, a magnitude of 5 and M2 was magnitude of 3, it would be 5 minus 3, which would be 2, so 10 to the 2. It would be 100 times more intense. I would be 100 times more intense than the earthquake I2 intensity. So when all is said and done, the intensities of two earthquakes can be compared using this formula. I1 divided by I2 equals 10 to the M1 minus M2. So example 2 says, how many times more intense was the earthquake in 1960 in Chile, magnitude 9.5, than the earthquake in 2005 in Chile, magnitude 7.8. We just basically subtract these magnitudes as shown, and we get a difference of 1.7. So if you enter that into the calculator, 10 to the 1.7 is basically 50 times more intense. The ratio of I1 to I2 intensities of these two earthquakes, the I1 was 50 times more intense than I2. Example 3, a major earthquake of magnitude 7.5 is 375 times as intense as a minor earthquake. So you have basically, you're given one of the intensities, and the value 375 is the ratio basically of the intensities, I1 over I2. So if you start with this formula, you can fill in the ratio of the intensities. The ratio of I1 to I2 was 375. You know that the magnitude of M1 is 7.5 minus the magnitude of the second. The second is going to be the smaller magnitude to give us this number greater than 1. So we have to solve here for x, so I have to log both sides, and we're using base 10. So when we log this side, log of 10, the value is just 7.5 minus x. So we get this equation here, and we can find, if we find we can bring the x to one side and the numbers to the other, we'll get this, and you can enter this in the calculator. It gives us negative, or it gives us 2.57. So 7.5 minus 2.574. Here's the value of x. So basically, the magnitude of the minor earthquake was 4.9. So take a minute to just look over that calculation. So let's move on to the loudness of sound. Again, this is a logarithmic scale with base 10. And the loudness of sound was originally measured in bells, named after Alexander Graham Bell. The current unit actually is decibels, which is equal to 1/10 of a bell. So the Bell scale, like the Richter, is logarithmic. A difference of 1 bell, or the equivalent is 10 decibels, corresponds to a factor of 10 difference in sound intensity. So a leaf rustling is about 10 decibels. So here's the scale here. And this is 10 times as loud as the threshold of hearing, which is down here, and they put it at a value of 0 on the scale. A whisper is 30 decibels, or 3 bells. This is 1,000 times more intense than the threshold of hearing. So let's look at example 4. We're completing the following from the chart above. Parasol is at 120 decibels, so really we've gone up from the threshold by 10 to the 12. And this is how many times as loud as a telephone dial tone, which is at 80 decibels. So 120, take 120 minus the 80, and we get 40. So this is in decibels, so it's gone up by 10 to the 4. It's 4 bells, so 10 to the 4 more or louder in intensity. And here's the calculation right here. A jet engine at 20 meters is 145 decibels compared to the threshold of pain at 125. So we can look at the numbers 145, 125. You can see it's a 20 decibel difference, and or if you look at here to here, it's a 2 bell difference, so it's 10 to the 2, 100 times louder a jet engine than the threshold of pain. So you don't want to stand too close to a jet engine, obviously. A whisper compared to a conversation. Whispers at 30 decibels, conversations at 60. So what's the difference? It's basically 30 decibels or 3 bells. Now we're going from a whisper. How many times as loud? Well, it's 30 decibels less. So we're looking at 10 to the negative 3, or 1 over 1,000. 3 bells compared to 6. So we're just going 3 minus 6. 3 minus 6, and we get negative 3. Okay, so if we're comparing the loudness of sounds, again we want to look at the decibels and intensities. Here's the formula if you're using decibels, comparing the intensities. To compare the loudness or intensity of two sounds measured in decibels, you use this formula. Notice the 10 down here. And notice we're using decibels minus decibels divided by 10, because we'll be using numbers like 40 minus 30 gives us 10 decibels. We have to divide that by 10 to convert to bells. But if you're already using bells, then it's just B1 minus B2. So this is the difference in intensities. Again, it's a log scale. Just have to subtract the difference in bells. This is the difference in decibels, but divided by 10 gives the same value. These two circles equal each other, obviously. Okay, class example 5. Given that decibel equals 10 log I divided by I0, show that the decibel level for the threshold of pain, 125 decibels, has a sound intensity of 10 to the 12.5 of I0. So basically, you're plugging in the values into this equation where decibels are 125, so that is here. And now we can divide both sides by 10, so we get this equation here. And now we can basically delog or do drop swing bump, drop the 10 down. Sorry, drop this down. Here it is here. The 10 swings over and bumps the 12.5 up. So the difference, or the ratio of intensities rather, is this, and I, the intensity of the threshold of pain compared to the threshold intensity is 10 to the 12.5 more intense. How many times more intense is the sound of piano playing, 67 decibels, than the whisper at 22? So you subtract, well, you're comparing how many more times intense is the sound. So I1 over I2 is 10 to the 6.7 minus 2.2. Now this value is in in bells. So remember that's in bells. Or if you'd used decibels, the numbers would have had to be divided by 10. So 10 to the 4.5 is 31,622. Two telephones in a home ring at the same time with a loudness of 80 decibels each. Does this mean that the total loudness is 160 decibels? Explain why or why not using sound intensities and the properties of logs. I'm not really going to get into any questions like this, but you can read over the calculation for your own edification here. Now if you're doing chemistry, especially chemistry 12, you'll soon know that the pH scale again is a log scale to the base 10. Every time you go up by 1 on the pH scale, you are decreasing in concentration of acid by a factor of 10. So less or increasing alkalinity in this direction to the right and increasing acidity in the direction to the left. The scale was introduced by a Dutch chemist, Søren Sørensen, in 1909, and really represents what it means is the power of hydrogen, how many hydrogen ions there are present in concentration. So the pH scale measures the range of hydrogen ion concentration by determining acidity or the alkalinity of a solution. The scale measures from 0 to 14, with values below 7 representing acidity, above 7 representing alkalinity. The value of 7 represents a neutral level in the pH scale, where the solution is neither acid nor base. Okay, let me just scroll down. So similar to the Richter scale, the pH scale is logarithmic. A difference of 1 unit, as I mentioned, is a factor of 10 difference in intensity. Therefore, if vinegar is a pH of 3, then it is 10 times as acidic as tomato juice. pH of 4, because if you go from 4 to 3, you're getting more acidic. And it's 100 times more acidic than normal rain of pH of 5. On the other hand, household ammonia, pH of 11.5, is 10 times as alkaline, more alkaline as milk of magnesia, which is pH of 10.5. It's 1,000 times as alkaline as seawater, which is 8.5. It's glad to see that seawater is a lot less alkaline. Okay, if we're completing the following using the table of values here, we can see that tomato juice, which is at 4, is how many times more acidic than pure water? Well, we're going from 7 to 4, getting more acidic by a factor of 10 to the 3, or 1,000. Eggs and pure water. Eggs are at 7, sorry, at 8, and pure water at 7. So eggs are more basic by 10 to the 1. The difference is 8 minus 7. Here it is 8 minus 7, so 10 times. Milk of magnesia and blood. And milk of magnesia is 10.5, blood is 7.5, so the difference is 3, so 10 to the 3. Milk of magnesia is 1,000 times as alkaline as blood. Vinegar is 3 compared to normal rain at 5. Difference is 2. It's getting more acidic. Vinegar is more acidic by 100 times, 10 to the 2. Eggs are how many times more alkaline than washing soda? Here is washing soda at 12. Eggs are less alkaline, and the difference is 4. So it's 1 over 10 to the 4, or you could say 8 minus 12, 10 to the negative 4, so 10,000th of a time as alkaline as washing soda. Okay, last few examples here. Comparing acidity and alkalinity of solutions. To find how much more acidic or alkaline one solution to another is, you use 10 and the pH of one minus the pH of another. So that's pretty straightforward. You guys are doing chemistry 12 and you should know all this stuff. If you don't know already, you can just basically subtract the pHs, and you know that if it's the pH of one is less than the other, it's more acidic. So I'll let you read over the answers here for these particular questions, or at least for number 9. The formula we'll be using very shortly in Chemistry 12, if we haven't already done so, is pH value is equal to the negative log of the ion, the hydrogen ion concentration. So if we have a concentration of, say, 1 times 10 to the negative 7, sorry, I have to pick my pen, we're going 1 log of 10 to the, let's see, the hydrogen ion concentration is 1 times 10 to the negative 5. Let me just tell you that water is 10 to the negative 7. So that might clue you into the fact that the pH is 7. Well, if we look at the pH here, equal to negative log of 10 to the negative 5, With this being a base 10, you know the answer to this is going to be -5, and this negative out front makes it +5, so the whole value is 5. The pH is 5. And if the pH was 7, you'd be taking negative log of 10 to the 7. So that's why it's pH 7. Well, this example says a patient gave a urine sample which was found to have a pH of 5.7. What was the hydrogen ion concentration? Here's the pH, so 5.7 equals negative log of the hydrogen ion concentration. We simply multiply both sides by -1, so this side is negative now. We take the inverse log of this and the inverse log of that, or the antilog some people call it. So that's just shift log. In other words, you're using the button that says 10 to the x on it. So when you do the antilog of this, you get this guy here, and then the antilog of this is really you're raising this to the base 10. So it's 10 to the negative 5.7. That's your calculation, and you get the answer here. So it's basically 2 times 10 to the negative 6 moles per liter. That's the concentration you've just figured out. Another one, determine the pH of a solution. If your hydrogen ion concentration is 3.4 times 10 to the negative 4, you're given the concentration, you just take the log of it, and then take the negative of your answer, and you get your pH. Okay, so that is all for this lesson, so please start the assignment in class, and we'll see you there.